Okay, everyone, welcome back. We're ready to move on to the next talk. So the next talk is from Olivier Catoni. Olivier Catoni is a senior researcher at CNRS, so the French Research Institute, and is now part of Université Paris-Saclay. So Olivier has authored many works on PAC-Bayesian theory and a lot of monographs too, which were massively cited in the morning. So he will tell us about dimension-free PAC-Bayesian bounds.
Thank you very much. I would like to thank the organizers for this very nice workshop on PAC-Bayesian learning. And the work I will present is brand new, and it's co-authored by Ilaria Giulini, one of my former PhD students. And I'm going to talk. I have to be closer, yes. So I'm going to talk about three related subjects using PAC-Bayesian bounds. The first one is a very simple but basic subject in statistics. It consists in estimating the mean of a random vector. So I will assume that X is a random vector in Rd, but the result could be generalized to separable Hilbert spaces. And the goal will be to prove bounds that will not depend on the dimension d of the ambient space. And a related problem is to estimate the mean of a random matrix from an IID sample made of n independent copies. And we will use these estimates to solve linear least squares regression problems. So the dimension-free assumptions I'm going to make are assumptions concerning the second moment in the two first cases and the fourth moment in the case of the regression setting. And so the obtaining estimators for the mean with sub-Gaussian behavior under weak variance assumptions, it has been a hot topic in the last years, and there are interesting and fundamental papers by Lugazi, Minsker, and Mendelssohn, for instance, about this, starting with the one-dimensional case. So the approach here will be not to tackle directly the estimation of the mean in a dimension higher than 1, but in estimating directional means by considering the unit ball of Rd. And in a similar way, for matrices, we will estimate this one-dimensional mean for each possible choices of xi and theta, and this will allow to control the operator norm of the difference between the estimated mean matrix and the mean matrix. And the idea to deduce results about least square is to remark that the least square risk can be written up to a constant, the expectation of y to the square, that does not depend on theta, in terms of the expectation of the Gram matrix and of the expectation of a vector that is y times x. So if we have dimension-independent estimates for the Gram matrix and for the mean of yx, we can deduce results for solving least squares in a high-dimensional space and also in a Hilbert space, infinite-dimensional Hilbert space. So what we have to do here is to have results that are uniform with respect to the direction theta. And to obtain this uniformity with respect to that direction theta, we will use a PAC-Bayesian bound. So the general form of bound I'm going to use is this one. For any parameter delta, that will be the confidence level of the deviation bounds, we'll be able to prove a result about a perturbed version of the empirical mean. So we are going to control uniformly an empirical process, but using a perturbation of the parameter feeder. And so we find this log Laplace expectation here that was already introduced in the previous talks. And so what is important, of course, the quantifiers are very important. The whole idea is to be able to prove a result with probability 1 minus delta that are valid for all possible choices of posterior measure rho. And as was already explained in previous talks, the complexity factor here is measured by the Kullback divergence between rho and a measure mu on the parameter space, a probability measure that has to be non-random, not independent from the sample. So mu is fixed and rho can be anything, and so it can depend on the values of the sample. So here we are going to specialize to Gaussian computations in a way that is very similar to the way margin bounds were proved by John Shaw Taylor and Langford for SVM, for support vector machines. So we are going to use this PAC-Bayesian inequality that is valid for any choice of rho and mu. We are going to use it for Gaussian perturbations of the parameter. And this will make it possible to have explicit computations. So rho theta will be the Gaussian measure with mean theta and covariance matrix 1 over beta times the identity. So here we are using perturbations with a covariance matrix equal to 1. And mu will simply be, so here of course we want we are looking for a result that is going to be uniform for any theta on the unit sphere. So as the posterior will be anywhere on the unit sphere, as a prior we will choose the Gaussian measure centered at 0 with the same covariance structure. And if we choose the identity as the covariance structure, it's because this will allow us to have a Kullback divergence term that will be the norm related to the norm of the parameter. And in this setting, this is what we are looking for. In a previous paper, I had explored the possibility to have here a covariance structure that is related to the Gram matrix, and this would lead to results that depend explicitly on the dimension D. So here I want results that are independent of the dimension, and so I will choose an entropy factor here, a complexity factor that is measured by the norm, the Euclidean norm of theta. So the complexity will be measured by a parameter that will be independent of a dimension. So now we've got to choose the function f. Yeah.
The previous slide, in the inequality, so the mu appears in the theta divergence. I can see that.
Sorry?
The mu
Yeah.
in the inequality appears in the theta divergence.
Yeah.
But as does it appear? Only there? So does the mu appear anywhere else than in the theta divergence in this inequality?
No, it appears. It's the only place where mu appears here.
Okay.
And so it's a sort of a weight. Mu will be a sort of prior weight you place on the parameter space, and it will be used to somehow measure the dimension of the parameter space. And the proof is quite simple. You have to compute the expectation of the exponential of the difference between the two sides of the inequality, and then using Jensen inequality or using the Danskar-Varadhan inequality, you can transform this into the expectation of you can integrate outside from the exponential, both with respect to the sample distribution and with respect to mu, and you integrate something that is equal to 1 because you have compensated for the expectation here. And then you use Markov inequality to prove the result here. Does it answer your question?
And there's no assumption on F.
It's in fact, it's more straightforward to prove this when F is bounded, but the idea is that whenever this inequality has a meaning, because things are integrable, you can even define in a weak sense. I think that if you define when F is not integrable, if you define this to be minus infinity as soon as the negative part of F as an integrates to minus infinity, it can be generalized. As long as it has a meaning, it can be generalized.
And the expectation in the first term on the right hand side, the expectation is over the theta prime and both theta prime and x.
No. No. Here it's the expectation with respect to x.
Which is mu.
Okay. So it's x.
Sorry?
So what is the distribution of x?
We are working in the first case here with the sample is made of n independent copies of a random vector x, and the expectation is with respect to the distribution of x. Is it okay? Sorry. So here it's the expectation with respect to x, and here it's the empirical mean. Is that okay?
Yeah, it's just that it's not in the form that we are used. It's okay.
In some sense, the PAC-Bayesian bounds can be viewed as a way to control the supremum of an empirical process, except that we don't control the supremum with respect to theta, but with respect to arbitrary perturbations of theta. But somehow, if you have to control the deviations of something that can be written as the supremum or the infimum of an empirical process, you can use this kind of PAC-Bayesian bounds. And so you can use this bounds as a replacement for concentration of measure inequalities. When you don't want to control a general Lipschitz functions of x1, xn, but a function that can be written as a supremum of an empirical process, something that happens quite often in statistics. So we are going to specialize this by making a series of choices. I already told about the choice of the perturbation, that will be Gaussian to be able to do explicit computations. And so now we have to choose f. So the most obvious choice of f would be to choose f of the form lambda times theta primes, the dot product between theta primes and xi. But if we do that, we will be able to control what we are interested in, that is the dot product of theta and of the expectation of x, but under assumptions where we will have exponential moments of this form, because here we have the expectation of the exponential of f. So if f is just the identity, it's just the dot product here times a scale constant, then we will have to make exponential moment assumptions that we would rather not make. So a trick to be able to work under weaker hypotheses is to use an influence function to obtain robust results. An influence function psi, so f of theta prime and xi is going to be psi times lambda times the dot product between theta prime and xi, and we will choose psi to be close to the identity, but psi would be chosen to be some sort of mean of converting exponentials to polynomials. So the exponential of psi of t should be bounded by polynomials. And the polynomials, of course, will be related to the Taylor expansion of order 2 of the exponential. And psi will be symmetric, bounded, and we want also in the list of things we would like to have for the inference function psi, we would like also to be able to do explicit computations of psi of lambda times theta primes dot xi when rho is Gaussian. So it's possible to find such an inference function. We can squeeze in a polynomial between the two functions minus log of 1 minus t. The two functions, there is a polynomial in between in the interval minus square root of 2, but we are going to, and outside from this interval, we are going to define psi to be constant. And if we do so, we have, since psi is a piecewise polynomial, then we can compute the expectations here, because when theta prime is a multidimensional Gaussian, theta primes times xi will be a one-dimensional Gaussian, and it's possible to make explicit computations of piecewise polynomial functions of a one-dimensional Gaussian random variables by integrating by part. So more precisely, if I define phi of m and sigma to be the expectation of psi applied to a one-dimensional Gaussian variable with mean m and standard deviation sigma, phi of m and sigma has an explicit, we can write it in an explicit form that can be computed, and that depends on the distribution function of the normal distribution. With a reminder here that is not very nice to look at, but that is simple to write in a computer program. And essentially the remainder here is small because this f of a minus square root of 2 plus something will behave like an exponential. So it's equal to m times 1 minus sigma square over 2 minus m to the 3 over 6 plus a remainder term that is explicit. So we can, with the help of the expression for phi, we can explicitly compute the perturbations outside from the inference function. And this way, we will turn polynomials, we will turn exponential moments into polynomials. So now I'm talking about this part of the PAC-Bayesian inequality that takes this special form here, and this is bounded by the properties of the inference function, by the log of 1 plus the first and second moment here. So using now the fact that log of 1 plus r is less than r, this is bounded by this quantity, where we have here the second moment in direction theta. That is somehow the variance term. The inequalities here are the study I am doing here is not centered. So I will explain later how to center the analysis, but so it's somehow the uncentered directional variance here. And here you have the total variance that is divided by the parameter beta that controls the size of the perturbation of the parameter that has been used. So at this stage, we can see that we will be able to complete our goal. We'll be able to estimate the directional derivatives uniformly in theta, the directional expectations uniformly in theta, and the bound will not involve the dimension d of the ambient space, and also it will involve only these two moments. So we will be able to have a result under weak variance assumptions. So if we put all these things together, we obtain the following PAC-Bayesian inequality. So for that is going to define in a first a confidence region. So with probability 1 minus delta for any feature in the unit sphere, this estimator of the expectation in direction feature will be less than the expectation in direction feature plus here a variance term here, and here you get complexity term here also if you want, and these two terms are related to the perturbation, so to the measure of the dimension of the parameter space. So then, if you assume that we know, but we have known finite bounds for these two moments of order 2, then we can optimize the choice of lambda and of beta in this way. And we will obtain, by working both for theta and minus theta, to have the reverse inequality. We are on the unit sphere, so we need to prove inequalities only on one side, because the inequality on the other side is obtained by looking at minus theta. So here we have a confidence region defined by the estimator, the directional estimator E of theta. And so this is a convex set. And for comparison, the concentration inequalities available for a Gaussian vector are of this form. And so you can prove it in different ways. This is the concentration inequality that is cited by Lugosi and Mendelssohn. And an interesting thing is that you can, if you don't know how to prove it, you can prove it just by using what I've already explained, but by removing the influence function and doing explicit computations with the Gaussian, if you assume that X is Gaussian. So the interesting thing is to see what we have lost by comparison with the Gaussian case. So we have lost the centering in the definition of T and V, because in the Gaussian case we have a centered second moment, directional and global here. We have lost adaptivity in T and V because we have assumed that T and V were known bounds. And we have a confidence region that is no more a ball. Here the confidence region is a ball center, that's the empirical mean. But here, as we have applied the influence function to the dot product of theta and x, I, we have a confidence region that is convex, but that is not necessarily a ball. But what is encouraging on the other hand is that the numerical constants are exactly the same as in the Gaussian case. So under the mild assumptions that you have second moments, you can find an estimator, but at least a confidence region, that we have the same diameter as in the Gaussian case, but that will not be a ball anymore. So now if you want an estimator, you can just pick a point within the confidence region. The confidence region contains the true expectation, so it can't be void. So there is at least one with probability 1 minus delta on the event on which the PAC-Bayesian bound is satisfied. There is you can find m theta within the confidence region, and when you look at so as you have, then you deduce from this that theta times the difference between m hat and the expectation of x is bounded by 2 times this quantity. Okay, so I have to speed up things quite a bit. But I think it was useful to explain the beginning in detail. So now you have this kind of bound for the Euclidean norm of the estimation error. And here you lose a factor 2, but in fact you use a factor 2 if you are very unlucky. You could reduce this 2 to square root of 3 by setting m hat to be the middle of the diameter of the confidence region if you want. And if you are lucky and the confidence region is not far from a ball, you should be able to have rather constant close to 1 here. Okay. So now the result is not centered, but you can center it by a sample splitting argument, quite standard. You take a small amount of the sample to have a pre-estimator, a coarse estimator of the mean, and then you work with the remaining part of your sample. And if you do that, you will have an estimator for the mean with an estimation error that will be equivalent to what you obtain with centered definitions of the moments here. Okay, so I will go fast on the rest. So you can do the same kind of things with matrices by controlling this kind of quantity with. So instead of in the vector case, you control the dot product of theta prime and mi, and here you have two parameters psi. So we are looking at matrices of size p times q, and by controlling this quantity, we can prove similar results for matrices. And the difference with vectors is that we will be able to study the operator norm of the statistical error. And so we can compute almost explicitly the estimator, the directional estimator. And we have a PAC-Bayesian inequality in which you have various terms that appears, and the largest one is the Hilbert-Schmidt norm of the matrix. And now you have to optimize the parameters, so, assuming that if you know bounds for the Hilbert-Schmidt norm of M, and for the operator norm of M times M transpose and M transpose times M, and of course for the variance term. And if you choose the parameters in an optimized way, you will obtain here for the operator norm, but this is going to give a result for the operator norm that is defined and in terms of these quantities, and what you gain with respect to a vector. So if you apply the result for a vector to a matrix, you obtain a result in Hilbert-Schmidt norm, because the scalar product for matrix gives the Hilbert-Schmidt norm. But here we have an improvement, and it's the fact that instead of having a complexity term of size t over v, we gain a square root here. So the directional estimate will be of order the square root of v times t over n, something that is lower than what you obtain for the Hilbert-Schmidt norm. Okay. So I will go very fast on the rest of my presentation. So one question you can ask is whether it's possible to adapt to the parameters I assume to be known in the beginning. And the answer is yes, to a certain point, by using asymmetric influence functions. So instead of squeezing the influence function between minus log of 1 minus t plus t squared over 2 and log of 1, I squeeze it between two terms, so that the exponential of psi is going to be squeezed between 1 over 1 minus t plus t squared and 1 plus t, and we have a linear, the upper bound is linear for the influence function. And so now we can estimate separately the positive and the negative parts of the dot product that we are interested in. And doing so, it's possible in the vector case to obtain estimators that will adapt. Where is the result? Sorry. We adapt to the values of V. So now we don't need to know V and T to compute the estimators, so we can choose V and T to be exactly equal to these two quantities. But the price to pay is increase in the constants here. But other methods to be adaptive, like Levsky's method, also lose a constant at least equal to 2. You can do the same kind of thing for matrices. I will skip it. And it's possible to do a special study for the Gram matrix, because the Gram matrix is a symmetric matrix, and it's defined by the quadratic form. We can look only at theta, the dot product of theta and g theta, instead of having two parameters here. And doing so, we can have an adaptive estimator. I will give you the form. We can have a confidence region for a Gram matrix with diameter here given by this. So I still need to know a bound for the fourth moment here. T is a bound for e to the for the norm of x to the power 4. I don't know if I read. Yeah, it's written here. So if we know this bound, but it's a bound bearing on the expectation of one-dimensional random variable, so one-dimensional expectation, then we can adapt to the directional moments of order 4 here, and have a confidence region whose the diameter in direction theta will depend on theta here, because it will be equal to the 1 over the product of this and this to the power 1 over 4. And so it provides a better estimation of all the eigenvalues of G. And you can, by picking up a matrix in the confidence region, you can have an estimator that is a matrix. And what you will control is the operator norm of the estimation error by doing this. So let me just tell you a word about the application to least squares ridge regression. So I'm going to discuss more generally ridge regression, where we allow a penalty of the form lambda times the square of the norm of theta, but lambda can be equal to 0, so it will cover also the case, the usual case. So as I explained in the beginning, the idea is to look at this risk function here. The risk is defined as a function of the Gram matrix and a random vector V. So now if you assume that you have estimators for the operator norm of G equal to G hat and for V hat, what I explained before will provide estimators of order big O of square root of log of delta 1 over delta over n, under the assumption that the norm of x to the power 4 is finite, the expectation of the square root of y times the square root of the norm of x is finite. So this means that if you have an independent noise, if you have a structure of the form y is equal to f of x plus a centered noise, then the assumption of the noise is only that the noise has to be square integrable here. And under these assumptions, by considering the estimated risk here obtained by replacing G and V by G hat and V hat, you can derive bounds that will be valid for in Hilbert spaces, not only in finite dimensional settings. So the most obvious bound is a bound obtained by optimizing in theta in a compact subset of RD, and then you can simply prove that you have a slow rate of order 1 over square root of n. Now, if you want to be a little more clever, you can look for a confidence region by looking at the difference, at the risk differences. If you look at the risk differences, you can bound it by a convex function, gamma of theta and psi, that involves the differences of the estimated risks, plus something that depends on the estimation error on the Gram matrix here, epsilon, and on the vector v here. And of course, sorry, there is a misprint here. It should be the hat should not be a hat here. What should be here is the minimizer of the true risk, not of the empirical risk, or of the estimated risk. Of course, for the true risk, this quantity here is always positive, so the minimum of gamma has to be at psi equal to theta, and so 0 has to be within the subdifferential of gamma when psi equal to the optimal parameter that we need here. So doing the computations, we found this confidence region that is defined in terms of theta hat is the minimizer of the estimated risk, and so the confidence region involves values of theta that are at a distance from theta hat that is measured like this. And when we see that, we can think of taking defining an estimator theta tilde that is the minimizer of the norm within the confidence region. And if we take this, we will obtain a fast rate for the estimation error. This is the true minimizing parameter here, but measured by a norm that is not we don't have a fast rate for the excess risk here, but the excess risk is the distance between theta tilde and the optimal parameter measured by the metric defined by the Gram matrix G. So here we have the metric defined by the square. Sorry, there is a misprint. Yeah, it should be G plus lambda times the identity. I made a mistake. It should be G times. Here it should be G times lambda I also, but we can't have a fast rate for the excess risk, but we have a fast rate for a modified measure of the distance between the estimated parameter and the optimal parameter, that consists in taking the square of the matrix that is here, that it should be G plus lambda times the identity. And then, for the excess risk itself, you deduce from this a bound where you have to divide by the lambda plus the smallest eigenvalue of the Gram matrix. So this is depending on D. And now you can study sparse recovery using this kind of tools also, but I don't have time to give you more details, so I'm going to stop here for the first part of the talk.
Thank you, Olivier. We have time for maybe one quick question before moving to the second part of this talk. Yeah.
Could you say a bit more about the intuition behind designing this influence function that you use? How do you come up with that?
Yeah, the intuition is to convert exponentials into polynomials by replacing the exponential by its Taylor expansions of order 2, as it can be seen on here. So what I want to do is to control the exponential of f. But I would like to have polynomial moments. So I would like to replace exponential f by its Taylor expansion of order 2. And to do this, we can do this by choosing for f a function of psi that satisfies this inequality, because then exponential psi will be less than. This is the idea. The idea is to turn exponentials into polynomials in one word.
Thanks, that's very nice, very beautiful. So I have one question about the deltas. So can you get these ones simultaneously for all deltas, or is it just for a fixed confidence delta?
The bound can be obtained for any delta, but the estimator depends on delta.
Oh, yeah. Right.
Because the optimal choice of the parameter lambda depends on the level delta here.
Yeah.
So if you don't optimize lambda, you can have results that will be, this one is valid for any values of delta, but if you take lambda fixed, you will lose something. It's the same as in the one-dimensional case that I published before. You can have results for different values of delta with the same estimator, but with a non-optimal value of lambda.
Is it possible to have something weaker than bound in second moment? So like first moment plus some epsilon?
I didn't write it down, but it should be possible to work with different influence functions. If instead of putting 2t to the square here, you put t to the alpha with alpha p to t to the power p with p superior to 1, the constants will not be the same, but you should be able to obtain a result. I didn't try to write it down, but it should be possible.
Okay, so let's move on to Olivier's second talk.
So I need
Just a
some
direct
help.
continuation of this one. So specializing the previous result to the estimation of the mean or random vector.
Okay, so thank you. So it's also a joint work with Ilaria Giulini, and the two preprints. This is a paper that has been submitted and accepted by NIPS. And what I talked about in the first talk is in a preprint, but is also available on my personal page and on archive. So I will come back to the question of estimating the mean of a random vector, and I will try to find a compromise between the simplicity of the estimator and the bound we can prove. And so the idea here is to apply the influence function to the norm of xi. So of course, if I apply the influence function to the norm, I have a much simpler estimator, because what I do is just thresholding the norm of xi. So I'm projecting xi on a ball of radius 1 over lambda. So here I can choose for the influence function psi the simple threshold function, that is the minimum of t and 1. Let's go to this. And I consider why I replaced each sample, xi, by its projection on the ball of radius 1 over lambda. Here, this is what it means. And I define the estimator of the mean as the empirical mean of the shrinked sample. And so the idea to exploit this setting are that so if I compute the difference between 1 and psi t over t, because what I'm going to have to control here is something of the form psi of t over t. So when psi is the simple threshold function, then 1 minus this ratio is always positive or null and is bounded by t to the power p times a constant depending on p, but this is valid for any value of p, be it integer or non-integer. And we have projected on a ball of radius 1 over lambda, and this means that lambda times the norm of yi is always less than 1. So the assumptions here will be that at least we have to have a bounded second moment. And we will assume that the directional variance is bounded by a known constant v. So it's the, yeah. Yeah, so m is a notation. Only v is known. Of course, m is not known. It's only a notation. M will be equal to the expectation of x. And so we have to choose a scale parameter lambda, and we will choose for lambda something depending, of course, on the directional variance here, as before. So I state the result first. If we do that, we have a simple estimator of the mean that satisfies. So we have two terms here that are the same as before, but with slightly increased constants. In the previous case, we have a confidence region that was not a ball, but here we had constant 2, here we have 2.4, and here we have a factor 4. And we have, so we have the maximum of the expectation of the norm of x minus the centered total variance of x and v. This is just if the estimation of v is, if the known bound for v is not too bad, v should be less than this quantity. But if it's not less, I take the maximum between the two. And the price I've got to pay for the fact that I have a simpler estimator are the remainder terms here. So the second one, C prime, is not a problem because it involves only the expectation of the norm of x to the power p. So I can take at least p equal 2, and I will have something in 1 over n that is of second order. So this one is always of second order. And this one is of second order also if I have a finite moment here for p a little larger than 1. And if I have only a second moment, then I have an additional term here that is going to be of a form that is going to be a little, but it's not shameful. I mean, you can it's just that you have the product of this with log, you have the product of these two at the same time. But so the idea is that if you have a little bit more than a second moment, if a moment of order a little bit higher than 2 is finite, then you get a bound whose leading terms are the same as in for Gaussian concentration, although the data are not Gaussian, of course. So, how many? I've got 5 minutes. Okay. So let me tell you a word about the proof. So of course the main ideas are the same as in my previous talk. And since I'm computing the empirical mean of a shrinked sample yi, I will have to compare the expectation of y with the expectation of x, and I can decompose the directional error between the expectation of x and the expectation of y, and the error between the empirical mean of y and its expectation. So for the first term, we can write explicitly what we have. Alpha is equal to what this scalar, the shrinkage parameter here. And so we can decompose it like this, and then use the fact that 1 minus alpha is less than any power of t of lambda time the norm of x to the power p. So we obtain this bound for the first term. And then the second term will be tackled using a PAC-Bayesian inequality. And here, what we've done, the PAC-Bayesian inequality I explained in the first talk, it involves the expectation of the perturbation of the parameter, rho theta, outside of the log. But we can put it inside because the log is being concave. It goes in the right side. So I have put using Jensen inequality, I've put the perturbations with respect to the parameter inside the log here. And then as the perturbation is Gaussian, we could use the explicit formula for the Laplace transform of the Gaussian to obtain this thing. So now here the theta prime is a Gaussian, so it's not bounded. But once I have integrated with respect to the perturbation with respect to theta, I get theta that is going to be on the unit sphere, so it's bounded. I have to compute the expectation of the exponential of a bounded argument. And then to do that, I can use the ideas in Bennett's bound. So the idea is to use the fact that this function is increasing, and this one also, and that they are equal to 1 at 0. And this allows to turn, as in Bennett's and Bernstein inequality, to turn the exponential into polynomials also. So now I've got something that is expressed as a function of the directional variance and of the total variance here. So for the total variance, it's quite simple because y is obtained by projecting x on a ball, so it's obtained by applying a contraction to x, and so a contraction will lower the variance. So the variance, the total variance of y is less than the total variance of x. And for the directional variance, it's not the case, but you can explicitly introduce alpha, the shrinkage ratio here, and use a convexity argument to relate the directional variance of y with the directional variance of x. And you will also have here our upper bound for 1 minus alpha. And if you put all these things together, you get this inequality for the directional estimation error. And then you optimize you optimize mu, lambda, and beta, and you get the proposition I've shown before. You get this inequality. So the summary is that by using a shrinkage estimator, you can have an estimator of the expectation of a random vector that has almost Gaussian concentration properties, and with a complex and in the bound you have no mention of the dimension d. So it's valid also, although I didn't write the proof in a separable Hilbert space. It should be also valid in a separable Hilbert space, for instance, in a reproducing kernel Hilbert space. And so that was, I think it's time to thank you again.
Thank you very much, Olivier. Additional questions, comments?
Yeah, I just had maybe a naive question. Yes, how does this was balanced compared to the already existing exponential inequality kind of distribution?
You have bound, for instance, we have a recent paper in Annals of Statistics by Lugosi and Mendelssohn, who used a median of means, a flavor of the median of means estimator. But the estimator is not easy to compute, and the constant you get here is equal to here outside of the. I think that outside of the square root you have a constant equal to 400.
And what's the bound, like Bernstein bound in the dimension? Your ski, how does that compare?
I don't think. I think that. I don't know of an equivalent, but maybe I'm wrong. But if Lugosi and Mendelssohn have published a bound recently with medians of means and a factor 400, it should be that. I mean, I think it's the state of the art, but maybe it's not. But,
I don't know, maybe there's some different assumption, but let's discuss this offline.
Yeah.
Other questions? Okay, well, let's thank Olivier for his nice 2 talks.
So thank you very much for your attention and invitation.
And so we now have the second coffee break, and again, poster session on the walls. And the next talk is at 3:30.
Ce que tu gagnes avec cette fonction aussi, c'est de te ramener uniquement au moment d'ordre 2 ou d'ordre 4 dans le calcul.
D'ordre 4 pour la régression.
Voilà,
hein.
pour la régression.
Oui, mais de toute façon, c'est l'ordre 4 pour la régression, c'est le terme de variance qui est d'ordre 4, donc on peut pas.
C'est aussi les hypothèses qu'ont Lugosi et Mendelssohn. Parce que du coup, tu faisais référence à quel papier? Parce que
Le dernier là qui.
Parce que je sais pas si tu l'as vu, il y a un papier en fait de Guillaume et il a 15 jours et où ils ont en fait des bornes de risque pour l'estimateur MOB. Je trouve qu'ils ont fait avec Lugosi. J'ai pas le temps de le lire, en fait je l'ai imprimé et je l'avais.
Oui, non, mais je sais qu'on peut faire des choses similaires avec le MOB, mais je pense que de toute façon les constantes seront. Enfin, l'avantage du MOB, c'est qu'il est adaptatif par rapport à la variance. Mais c'est comme les méthodes adaptatives, que ce soit les ski et trucs, on perd une constante.
Ouais. Et puis surtout, c'est vachement compliqué.
C'est plus calculé.
Bah, c'est ça.